Hello, this is section 4.3, using the first derivative. We're going to look at to see how a function is increasing, decreasing, and we're going to also test for a local extrema. Okay, so this section is important because some of the next sections in this section will build upon this material. So please make sure that you understand it, and if you have any questions, feel free to ask. So for starters, if we look at a function, how do we tell if the interval is increasing or if the intervals are decreasing? So when we use this test, we're going to be able to figure that out. And by looking at the graph over here, here is a function. And to see if something's increasing or decreasing, if we take the first derivative, then we get the tangent line, right? So the tangent line for this is positive slope. And for this piece here is a negative slope. And for this piece here is a positive slope again. So if you take the derivative of the function, it'll tell you if the slope is increasing or decreasing or what's going on. So if we look at that tangent line, we can see that this function is going up until we get to about x equals 2. And then it's going down until we get to x equals 4. And then it's going back up again. So we are going to use the derivative to figure out if we are increasing or decreasing. Okay, so the theorem. Given f of x is continuous on the intervals a, b, and differentiable on a, b, and not including a, b, if the derivative of x is greater than 0 on AB, then the function is increasing. So once again, if the derivative of the function is greater than 0 or positive, then the function is increasing. If the function is negative on those intervals, if the derivative of the function is negative, then we're going to see that the derivative or the original function is decreasing. So once again, if the derivative is positive, the function's increasing. If the derivative is negative, the function is decreasing. Alternatively, it is also acceptable to write the intervals as open rather than closed. Okay. To find an interval where the function is increasing or decreasing, we're going to use what's called a sign chart for the derivative. Okay. So the steps, we're going to find all critical points. A critical point is where the derivative equals 0 or the derivative does not exist. Then we're going to make a sign chart for that derivative. And once we make the sign chart, we're going to use test points around the critical points. So we're going to set up a chart around these critical points, and then we're going to find values on the left of the critical point and on the right of the critical point. Okay, at that point we can determine if we plug in that test point and it comes out negative, then my function's decreasing. If I plug in the test point into the derivative and it's positive, then I know my function is increasing. So that brings me to the next thing. If you have the first derivative test, if the derivative changes from positive to negative at C, then we have a local maximum. So guys, that looks like this. If it's increasing and then decreasing, we have a max. So think of a mountain, so once again, this was positive slope, negative slope, right? That gives me a max. If the derivative changes from negative to positive, so here's negative to positive, then we have a local minimum. Okay, so once again, that looks like a valley. If the derivative doesn't change signs at C, then the function at C is not a local extreme value. So it's not a big deal. We'll still get information to see if the function is increasing there or decreasing. So for instance, we have an example underneath here. Let's say I found 3 critical points. So here they are. And I look at the value on the left of the first one. I found the derivative, I plug in that point, and I get a negative. I know my whole function's decreasing. And then let's say I'm looking at, this first one, I'm going to highlight it here, and I'm going to look on the right of that critical point, and I plug that value into the derivative, and let's say that that value comes out positive, then I know my function is increasing. The second critical point, I'm looking on the right-hand side of that. So I have some value on the right-hand side. I plug it in. Let's say it comes out negative. Then I know my whole function is decreasing. And then finally, the last critical point, I'm looking on the right of that. So I'm looking at a value on the right of the critical point, and I plug it into the derivative. And if that comes out negative, I have that my whole function is decreasing. So this is giving me some really great information. Whenever you see a switch, like I'm seeing a switch here from down to up or decreasing to increasing. So once again, if you make a chart, it's going to give me a minimum. Now I have going up or increasing and then going down. Then you have a maximum. And then here's an example where there's no change. We're going down, and then we're going down again. That means no local extrema. But we still know that the function's decreasing around that last critical point. Okay, so let's look at an example so we can put the pieces together. These examples are going to have you graph them, so it's important to get as much information as you can before you do that. So it says, find the domain, the end behavior, the intercepts, the intervals where f of x equals x to the fourth minus 4x cubed is increasing, decreasing, and any local or absolute extrema. Then sketch a graph. Okay, so let's start with number 1. The original function is f of x equals x to the fourth minus 4x cubed. Okay, the domain of this, because it is a polynomial and I'm not dividing anything off, is all real numbers. So the domain is negative infinity to positive infinity. Okay, that's good because I don't have any holes. The whole function is continuous. So I found the domain. Now let's look at the end behavior. So I don't know if you remember from the limit section, if I take the limit as x is approaching infinity, and I plug that in to the function, let's see what happens. I have infinity to the fourth power minus 4 times infinity to the third power. That's going to give me infinity. Okay, so positive infinity. So I know at the end of my function, as x is approaching infinity, my function is going to be going up towards infinity. So let's check the other side. The limit as x is approaching negative infinity. So once again, you're going to plug that in to your original function, which was x to the fourth minus 4x to the third, and I get negative infinity to the fourth power minus 4 times negative infinity cubed. Negative infinity to the fourth power gives me a positive infinity, and then a negative times a negative is another positive infinity. So we get positive infinity. So as x is approaching negative infinity, I know my whole function is going up again to infinity. Okay, next it asks me to find the intercepts. Okay, so if I find the x-intercept, I gotta let y equal 0. So I get 0 equals x to the fourth minus 4x cubed. I factor out x to the cube and I get x minus 4. And I set that equal to 0, so x cubed equals 0. And then also x minus 4 equals 0. So x equals 0 and x also equals 4. So this particular graph is going to go across the x-intercept at 0, 0. And then again, it's going to cross it again at 4, 0. Okay? Now to find the y-intercept, I have to let x equal 0. Okay, so y equals 0 to the fourth minus 4 times 0 cubed. So y equals 0. So once again, we get that intercept of 0, 0. All right, so I have my intercepts, so let me go ahead and put a box around them because we need all this information. We got the domain, we got the end behavior, we also, got the y-intercept, which is also the x-intercept. So let me go ahead and highlight what we found so far. This is my end behavior. Here's my intercepts. And I'm going to go ahead and place a check mark up here because I found the intercepts. Okay. Now it says find the interval where the function is increasing or decreasing in any local or absolute extremia. Okay, to find where the function is increasing or decreasing, I have to do one, I have to find the derivative. 2, I'm going to have to set the derivative equal to 0 to find the critical points. Okay, and then 3, I'm going to create a chart. And it's called a sign chart to determine where my function is increasing or decreasing and where we have local max, a local maximum or a local minimum. Okay, so those are going to be my steps. So the first thing I'm going to do is part 1 here is I'm going to go ahead and find the derivative. So once again, the original function was f of x equals x to the 4th minus 4x cubed. If I find the derivative of that, I get 4x cubed minus 12x squared. Okay, so I did part 1, which was find the derivative. Now I'm going to have to set this equal to 0. And the reason why I'm doing that is I'm looking for my critical points. Okay, so if I factor out a 4x squared, I'm left with x minus 3 equals 0. So if I set 4x squared equal to 0, I get x equals 0. And if I set x minus 3 equal to 0, I get x equals 3. Okay? So I have my 2 critical points. My critical points are when x equals 3 and when x equals 0. Okay, so I'm going to do the chart on the next page. So I'm going to read over. So my critical points, once again, are when x equals 3 and when x equals 0. Okay, so I have 2 critical points. All right, so I'm going to make a sign chart. Okay, so since I have 2 values, I'm going to put them in order. So my first critical point is when x equals 0, and my second critical point is when x equals 3. Okay, so once again, I have 2 values. Okay, so what I'm going to do is I'm going to create this chart. The first row is going to be my test point, and then I'm going to plug my test point in, and I'm going to call this TP, right? So I'm going to plug my test point into my derivative and see what the result is. Is it positive or negative? And then my next row, let's make this look a little bit neater. I'm going to say if the function is increasing or decreasing. Okay, so this is what my chart looks like, and this is what I'm going to do. All right, so the first thing I got to do is I got to find a test point that is a value on both sides of the critical point. So if I look at this, you know, I have x equals 0. I'm going to put x equals -1. That should be easy to plug in. And then on the right of my critical point x equals 0, I'm going to plug in the value of 1. And then on the right of my critical point x equals 3, I'm going to plug in a value of 4, let's say. Okay? So the first one, my test point is -1. And then I chose 1, and then I chose 4. So what I have to do is I got to plug this into the derivative. And just to remind you of the derivative, it was let me just peek at my notes really quick. 4x cubed minus 12x squared. Okay? All right. So we plug in -1 into that formula. So we get 4 times -1 cubed minus 12 times -1 squared. And that is a squared there. Okay? So if I take -1 cubed, I get -1. So basically get -4. And -1 squared is a positive 1. 1 times a -12 is a -12. So I basically get -16. This is negative, right? So I can go ahead and say it's negative, so that means my function is decreasing. Okay? Function is decreasing because it's negative. That's why. Okay? All right, let's look at x equals 1. So once again, we're going to plug this into the derivative. So I get 4 times 1 cubed minus 12 times 1 squared. 1 cubed is 1. 4 times 1 is 4. 1 squared is 1. 1 times -12 is -12. So I got a negative on this one too because I got a -8. So since I got a negative value, then I know my function's decreasing here. Okay, now I'm going to plug in x equals 4 into the derivative. So I get 4 times 4 cubed minus 12 times 4 squared. So 4 cubed, 4 times 4 is 16. 16 times 4 is 64. So I get 4 times 64, and then 4 squared is 16 times 12. So I get 192. And if you do 4 times 64, you get 256 minus 192. And if you do that math, you're going to get a positive value. Okay? So I know my function is increasing. Okay? So let's look at this. Around critical point x equals 0, on the left of that, the function is decreasing, and on the right of it's decreasing as well. So I do not have a max or a min. However, around critical point x equals 3, I see around that point I am decreasing and then increasing. So if I'm decreasing and then increasing, I get a local minimum when x equals 3. Okay? All right, so we have all the information. All we have to do now is graph this. So we're going to use all the information that I got so far to create this function. So what I'm going to do is I'm going to go ahead and put the values in here and then move on from there. Okay, so if I go back, I know that the function is continuous. I know at both ends of this it's going to reach positive infinity. I know I have some intercepts which are 0, 0, and 4, 0. And I know now where my function is increasing and decreasing. So let's go ahead and put some of these values in here. Okay, so I'm just trying to draw this out, and it's it's not going to be perfect, but we're going to get a general gist of what everything looks like. Okay, so here's the x-axis, here's the y-axis. That's all drawn out here. Okay, so x and y. All right, so my intercepts were 0, 0, 1, 2, 3, 4. This is 4, 0. So I'll just make a little note. 4, 0 here. This one's 0, 0. Okay. I know when x equals 3, I also have a critical point. So let's talk about what we know. We're going to go back for a minute. To find where that local minimum is, you're going to have to find your y value. So if x equals 3, I'm going to plug this into my original function. And my original function was x to the 4th minus 4x cubed. So if you plug in 3 into that function, you get 3 to the 4th minus 4 times 3 cubed. Okay? And I'm going to do the math quickly, but if you plug it into your calculator, you're going to get -27. So that critical point, or that local minimum, is at 3, -27. Okay, since my chart's not going to go down that far, so what I'm going to do is I'm just going to make a little break in the y-axis, and I'm going to make this 27 negative. So that point is going to be right here. Okay, so I'm going to put in that point 3 comma negative 27. I also know from the end behavior that my function is going off to infinity over here, so I know it looks like that. And then remember, my function is actually decreasing, right? So it's decreasing on the left of 0, and just to show you really quick, you know, the tangent line is decreasing. So that's what they mean by that. So let me erase that piece. Okay, so now the function's decreasing again, so it's going down. So once again, we want that tangent line to be decreasing. And then we have this local max, or local minimum rather, at x equals 3 negative 27. So now I have to swing up because my function's increasing, and then remember it's increasing onward. So this is, you know, roughly what my function looks like. Once again, I used the information that we gathered to create this graph. So that's what you're going to do. So once again, you know, we can see that there's a local minimum right here, what I just covered over in blue. I also see the functions decreasing on the left of 0, decreasing on the right of 0, and then increasing on the left, or excuse me, on the right of 3 and onward. It's increasing again. Okay? All right. So there's your graph. We're going to definitely have a part 2 of this section, so I will show you example number 2 and example number 3 as well.